Hi, and welcome back. In this video, we'll be answering the question in the title of the video. How many different ways can I decorate my wall? Because with mathematicians, of course, we really need to know what we mean by this question. We need to understand the rules of the game, as it were. So, firstly, we really want to know how many different symmetry groups there are for wallpaper patterns, as the actual pattern doesn't really matter so much to mathematicians. For example, these two patterns are different, but as we saw in last video, they have the same symmetry group, so we don't want to count them separately. Secondly, we don't want to have to do an infinite amount of work when designing our wallpaper, as this would incur an infinitely large bill for our hired artists. So, we need there to be a finite fundamental domain. And we will exclude patterns with an infinite fundamental domain like these ones. Of course, these patterns are interesting in their own right. It turns out the existence of a finite fundamental domain is precisely equivalent to there being two independent translations, i.e. two different translations which are not just multiples of one another. We call such symmetry groups wallpaper symmetry groups, since they're particularly good for designing wallpaper. Okay, so our question in total then is, how many different wallpaper symmetry groups are there? That's the question we'll answer in this video. In order to write down all of the groups, we want a labeling system for symmetry groups that gives different names to different groups. We've seen that labeling just the generators is not enough, as some patterns have the same number of the same type of generators and yet have different symmetry groups. So, what do? We instead use a different, clever labeling system invented by the famous mathematician John Conway. The clever idea that Conway uses is to note down different features of the pattern which correspond to generators, but also include information about relations, such as mirror line crossings, centers of rotations, etc. Given a pattern, we will write down all the features that we can find, starting with the most powerful, until we have a generating set. Since every single wallpaper group has two translations already, we won't bother noting these ones down. Then, if two patterns have different features, we will see their symmetry groups must be different. Therefore, noting down the features is a good way to make sure that the symmetry groups we find are different from each other. Okay, we'll now go through how to note down all of the different features, using Conway's notation. Firstly, if there are reflectional symmetries, we note down an asterisk, and for each distinct crossing of mirror lines, we write a number afterwards, indicating the number of mirror lines that cross there. We consider mirror crossings to be distinct if there is no symmetry taking one to the other. For example, in this pattern, these two crossings are not distinct, as a translation upwards maps the bottom crossing onto the top one. In fact, there are exactly three distinct mirror crossings here. Here, here, and here. And the number of lines at these crossings is 6, 3, and 2 respectively. So, we denote this group by asterisk 632. How do we denote the symmetry group of this pattern? Well, it would be asterisk 442, as there are three distinct crossings of 4, 4, and 2 mirror lines respectively. Note that in both cases we've found a generating set, so we don't need to continue noting down features. It may be the case that there are different reflections that do not cross each other. For example, take a look at this pattern. Here, as long as there are no other non-translational symmetries, we will use the notation asterisk asterisk to indicate the two different mirror lines. Okay, so once we've labelled all the reflections of a pattern, we need to move on to rotations. Many rotations, of course, can be explained by mirror lines, but as we saw before, whenever we combine two reflections to get a rotation, the rotation is around a crossing of mirror lines. So once we've drawn on the mirror lines, if we can see any other rotations that are not centred on crossings, these are new rotations that are not already accounted for. To denote these, we just write a number for each centre of rotation, corresponding to the order of that rotation, i.e. the number of times the rotation must be performed to get back to the identity symmetry. If there are also reflections, we write these rotational numbers before the asterisk to avoid confusion. For an example, look at this pattern. There are no reflectional symmetries, and there are 4 distinct centres of rotation. Here, 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 and here. Each of them is ordered 2, so we denote the group 2, 2, 2, 2. How about this one? This one has 1 crossing of mirror lines and 1 rotational centre, each of order 3. So we denote the group 3 asterisk 3. As an exercise for you, consider what the labelling of this pattern should be. It might be the case that we have marked on all the reflections and rotations, but this still does not account for all of the symmetries. For example, consider this pattern. It has 2 mirror lines which do not cross, so one might be tempted to say that it has symmetry group asterisk asterisk, as with the previous example. Actually though, these 2 mirror lines are the same under a diagonal translational symmetry, so this is wrong. Perhaps it is just a single asterisk. But then there are more symmetries to catch here. Note that this is the fundamental domain, and it cannot be used to tile the pattern with just that reflection and the 2 translations. There is another symmetry here, a glide reflection. A clever way to notice this is that we can link a fundamental domain to a reflected fundamental domain without crossing a mirror line. Conway calls this feature a mirrorless crossing and marks it with a cross. Therefore, for this pattern, we write asterisk cross, because there is 1 reflection and 1 glide reflection needed to generate the group. It is possible to have several different mirrorless crossings. Consider, for example, this pattern, which has 2 different mirrorless crossings and no reflections or rotations. Therefore, the group is denoted cross-cross. Note that these 2 glide reflections generate all the other symmetries, in particular the translations. Repeating one of the glide reflections over translates up and to the right, and doing one after the other translates in the other direction. Therefore, we have found enough features to generate the entire group. Finally, it might be the case that there are no rotations, no reflections, no glide reflections. But we know there are always translations, of course. In this case, if there are absolutely no symmetries at all other than the translations, we use the notation O for the group, as there are no symmetries. And we need to call this group something. Here is an example. Though we don't prove it in this video, it is the case that patterns with different combinations of features have different symmetry groups. Therefore, to know how many symmetry groups there are, we need to work out which combinations of features are possible. Okay, so which combinations are possible? This is our big question. Fortunately, there is an incredible theorem that is so magical it is scarcely believable, so much so that Conway calls it the magic theorem. It is the following. We assign a cost to each feature according to this table. For example, the cost of a asterisk is 1, the cost of a cross is 1, and the cost of a rotation differs depending on the order. For example, a rotation of order 2 will cost 1/2. Then, the possible symmetry groups are precisely the ones with features whose cost adds up to precisely 2. That's it. Okay, let's systematically work through all the possibilities to see this in action. Obviously, by this table, an O costs 2, and so we can't afford any other features if we have that. Also possible are the groups cross-cross, asterisk cross, and asterisk asterisk, as these clearly add to 2 as well. We've seen these groups before. Which groups are possible using only rotations? Well, if there are 4 different rotations, the only way to afford this is to choose the cheapest rotation, 2, each of which costs 1/2. And the only possibility, therefore, is 2, 2, 2, 2. There is no way, of course, that 2 rotations can add up to the full 2, because each rotation costs less than 1. So if we want to use only rotations, and we don't want to use 4, we need 3. It is left as an exercise for you to see that the only combinations that will work are 3, 3, 3, 4, 4, 2, and 6, 3, 2. Examples of patterns with these symmetry groups are shown here. Okay, what about if we only use reflections? An identical argument to the above shows that we can only have asterisk 333, asterisk 442, asterisk 632, and asterisk 2222. Note that the reflectional numbers cost exactly half as much as the rotational ones, and the asterisk uses up 1 of our cost, so this just follows exactly from the argument above. Okay, so far we've managed to find 12 different symmetry groups, shown here. We can, of course, combine rotations and reflections as well. I think it's best to leave these other possibilities as an exercise to you, as it's fun to figure out the names of the groups and what they look like. To help you out though, the other possible symmetry groups are displayed here. These are examples of wallpaper patterns with these hybrid symmetry groups. Try to figure out what the symmetry groups of these examples are, and match them up to the other possible combinations of features that you can try to work out yourself by getting the cost to add up to precisely 2. These extra 5 hybrids bring the total number of wallpaper symmetries to 17, which is the full number. There is, of course, deep and interesting mathematics behind this ridiculous whimsical theorem, which is beyond the scope of this video. Patterns like the ones shown in this lesson have been used for many thousands of years as decoration for buildings, objects, floors, walls, and ceilings. For example, these are all patterns found in Egyptian tombs, showing that the Egyptians had a very good grasp of different symmetry possibilities, thousands of years before groups were formalized. Purportedly, all 17 of the different symmetry groups may be found in the spectacular Alhambra Palace in Granada, South Spain, built by the Moors in the 14th century. The beautiful symmetric mosaic patterns that you can find within, some of which are displayed here, were the inspiration for many mathematicians and artists alike, including M.C. Escher, whose works display many of the same symmetries. Finally, the use of a fundamental domain is convenient for infrastructure, as making many of the same tile is more convenient than making many different tiles. As a result, many different symmetry groups can be found in the paving and brickwork as you walk around urban landscapes. Have a look for them. Okay, there are many exercises now for you to tackle, many of which I've mentioned already during this talk. Please give them a go, as it will reinforce your understanding, and in the case of finding the symmetries of a pattern, is also pretty enjoyable. In the next video, we'll be taking symmetries to the next level by considering symmetries in non-Euclidean worlds. See you then!